Everyone, we are back and we are going to go through our problem set to solution video. So let me get my pen and then we can go ahead and get started. I'm also going to open up Mathematica again. I'm solving Mathematica just because it's the programming language that I use. You'll learn a lot of different programming language, Python, etc. But the key thing is, again, we want to follow our problem solving steps and we want to show our work and we want to get to our fundamental equations. So we have a mass of 170 kilograms, this mass 1, that is attached to the scaffold. Our scaffold, again, is our black rectangle. There's attached to a wire and a spring. So our wire here, our spring here, with a spring constant of 35 Newton meters. Mass of the scaffold can be ignored. So again, we want to idealize our system. So we're going to ignore the mass. We're also going to ignore any frictional effects. And that is pretty much it. We're going to also assume that we also have some tension, or actually the mass is attached to the wire here, but yeah, so we can go ahead and get started. So first thing we do, coordinate system, after our idealizations, so we have plus. Now, free the body, so the body is the scaffold, from the surroundings. So we have some, I'm going to call this tension 1 here. There's also going to be, at this particular location, this body is going to have a weight 1. Weight 1 equals mg, m1g. And that's it. If you look at this body in particular, in the body, there's going to be basically our weight 1 going down and our tension that's going to be going up here. But if we look at here, it's just basically, you can kind of look at the tension going the other way, to keep that in equilibrium. But again, it's hanging essentially from that weight 1 there. So we also are going to have some, I'm going to call this force from the spring. And we know that that is going to be equal to K delta X. So, fantastic. So, because the body is going to be right down here, it's going to point in the other direction. And ideally, the spring is probably going to have some elongation as well. We know what K is, so now we can start to write out our fundamental equations. So sum of the forces. So what are our unknowns here? We need to solve for the tension of the wire, the force of the spring, and the elongation of the spring. So we need to solve for this, and thus this, and then this. So we have 2 unknowns effectively, so we need 2 equations. So sum of the forces in X equals 0. There's no forces in X. Sum of the forces in Y equals 0 equals tension 1 plus force in the spring minus the weight 1. And then finally, sum of the moments, and I'm going to say sum of the moments about 1. So I'm going to pick my origin, right here. So the perpendicular distance from the line of action will be, and that's minus, equals 0, equals minus weight 1 times 3.5 meters. And then it's going to be plus force of the spring times 11 meters. Because again, perpendicular distance, line of action, we've got it. So let's go ahead and solve. 2 equations, 2 unknowns. So I'm going to say that K is equal to what? K is equal to 35. Mass 1 is equal to, I think, 170 kilograms. Yep. Weight 1 is equal to m, and then I'm going to define g here as well. G equals 9.8 m times g, and then we have fx equals t1 plus fs, and actually let's define fs too. Fs equals k times del x. T1 plus Fs minus W1, and then set this equal to 0, and then we're going to have, actually I want to look at this equation too, and then I'm going to have M1 equals minus W1 times 3.5 plus Fs times 11, set that equal to 0. Then I'm going to solve. I'm going to solve Fx, M1, Shift Enter. Let's go ahead. Actually, let's keep for now. Let's just solve for what Fs is. So actually, I'm going to go ahead and I'm going to clear Fs. even though it shouldn't matter, actually. Ooh, that's what it is. M1 here. So forget about that. And there we go. Tension, del X, and then we could also solve for Fs here. So we got it. Fantastic. So the next problem, it's kind of similar to our problem that we had, which is the kind of ladder problem. But now both of the surfaces have the same coefficient of friction. We have the mass of the ladder. So I'm going to call that mass ladder equals 20 kilograms. The length is 10 meters long, which we see here, and you can calculate from your geometry. Coefficient of friction, what's the maximum amount of force can be applied right before the ladder moves. Also, the weight acts at the same location as the force is applied. So we have to consider friction. We have to consider the mass of our ladder. That's pretty much it. So let's draw our X and our Y, positive moment. Free body diagram. So we're going to free the body. So our body looks like this. From the surroundings, there's going to be, I'm going to call this point 1. I'm going to call this point 2. So there's going to be a normal 1 here. There's going to be a normal 2 here. If we're being pulled here, again, friction, typically static friction is going to oppose motion. So basically it's going to point in the other direction, because if I pull it out here, it's going to oppose the direction of motion. So it's going to be mu s n2. And then this is going to be opposing the motion. So when I pull it like this, it's going to drop down. So it's actually may point here. Again, it doesn't matter too much. You'll get the right values in the end, mu s n1, from this normal here. There's also right here, we have the weight, and we also have a force. So that's our free body diagram. So I am going to now do that the sum of the forces. So what do we know? What do we not know? So weight equals mass of the ladder times g. So we know that. We don't know what this force is that we're solving for here. We do know mu s. So we need to solve for N1, N2, and the force. So we need 3 equations. So sum of the forces in the x equals 0, which are going to be equal to our N1 plus force minus mu s N2, set it equal to 0. Sum of the forces in the y, which are going to be equal to 0, which is going to be equal to mu s n1, and then that's also going to be minus weight plus n2. I believe that's it. Yes, it is. And I'm going to do some of the moments. This is going to be the difficult equation to write. So where can I cancel out? They're all pretty much equal. So what I'm going to do is I'm going to cancel out. Where are we at here? So I'm going to cancel out. Where should I? I'm going to pick my origin here at 1. Sum of the moments about 1 must be equal to 0. So now this is where we want to look at where we're going. So let's take it one step at a time. So we need to look at the perpendicular distance from the line of action of our forces. So let's see here. We can go ahead and get this started. So the perpendicular distance from the line of action of our forces, it is going to be this distance right here. So if we look here to here, so the perpendicular distance from our origin to the line of action of this force is just going to be this distance right here. So what is that distance? Well, we have this triangle here. So if I look at this origin, we know that this is 5. We also know this angle here, because it's given in the problem. And now we can just calculate what is that distance. So the perpendicular distance from the origin to the line of action. So that's just going to be this distance right here. And we know from this angle, this is our hypotenuse, so we're adjacent. So that's going to be this distance here. So we can go ahead and find that right now. Actually, I'm going to call this angle theta 1, and this is angle theta 2. So this angle theta 1. And if I look at my right-hand rule, I can indeed curl in the direction of that force. So it will lead to that, so the positive. So I'm going to go ahead and say that this is going to be positive F times, actually, yeah, because that's our force, times the distance, which is going to be basically, when we solve this one right here, we're solving for x. So let's go ahead and do cosine of theta equals x over 5. So it's going to be times 5 cosine of theta 1. So that's our first force. That's our distance. We got it. What about this one right here? So the perpendicular distance from the origin to the line of action will basically be this distance here. So that's going to be, so if I look at that here, and that will actually give us, I believe, a negative, because if I look at that origin, yeah, we have to flip our direction in order to curl it. So the perpendicular distance from the line of action will be just this. So that's going to be this distance here, which is going to be now sine. So it's going to be minus weight times sine of theta 1. Good. Now let's kind of erase here because it's getting a little messy. Let's do the same procedure. So remember, just to kind of walk this through again, this is the line of action of my force. I go from the origin. What is the perpendicular distance here? So again, that would just be this distance here. If I do the line of action for here, it's just this distance here, which is equal to here. And you see I have to flip my minus w. And this should be 5 as well. Minus 5, because it's, again, this distance here. Perfect. So we've got this here. Let's do this one here. So what about here? So if I look at the line of action first of this guy, the perpendicular distance will just be what? Now my triangle changes. So instead of this 5 now, it's actually 10. So 10. And then now, same angle, theta 1. So that doesn't change. But now this changes. So now I'm just going to do, and actually it's going to flip. So it's going to be minus mu s n2 times 10 times cosine. Actually, excuse me. Yes, that is the perpendicular distance from the line of action. The perpendicular distance from the line of action is 2 cosine of this. And then for n2, it's just going to be this distance here. As we can see, line of action, same thing. Except now we're going to have positive plus n2 sine of theta 1 times 10. Again, that 10 comes from the value here. Whew! It's a tricky little problem, but it's a very, very good one for you to kind of practice on and really apply that, that system. So let's go ahead and let's solve this problem now. So I'm going to go ahead and quit my kernel. And let's go ahead and let's do, so we're going to define, first of all, weight is going to be equal to, actually, what's our masses here? So let's go back. Let's look at our system. Let's look at what we got here. Let's go here. So I'm going to say that my mu s is equal to 0.4. My mass equals 20. My g equals 9.8. My weight equals mass times g. Good. That's all we really need there. And now we can go ahead, look at our expressions, write it up here, and we can get moving. So fx equals 0, set that equal to n1 plus f minus mu s times n2. There we go. That's one equation. Fy equals 0, which is also equal to mu s times n1 minus w plus n2. And then finally, m1 equals 0. Set that equal to f times 5. Actually, we'll define. We need to find our angles here. Actually, I'm just going to type it in each time. Actually, I'm not going to type it in each time. So let's go ahead. I'm just moving my recording mic here. Let's do theta 1, or theta equals 36.87 degree. Good. And let's go ahead. 5 times cosine of theta minus w times 5 times sine of theta. And that doesn't change anything, but now I got minus 10 times mu us times n2 times cosine of theta. And then we have finally plus n2 times sine theta times 10. And then we're going to solve once we check that our equations look okay. Fx, Fy, M1. Once Mathematica. All right, what are our unknowns? F and 1 and 2. That seems to be pretty correct. We got it all. And there we go. So we anticipated the directions correctly, and we can only apply 23 newtons before basically we start to go to 0. Fantastic. Difficult problem, but again, break it down into steps. Try to make sure you have that geometry. Remember, the moment is the perpendicular distance from the line of action of the force. You got it. Have a good one. Thanks. Bye.